At this point, we've looked at several circuits that have batteries in them, and we've always just treated the battery as a source of voltage. But it turns out there's a lot more going on inside a battery than just that. So at the core of every battery is a source of voltage that will cause current to flow. And this voltage is called electromotive force. Or for short, we just call it EMF. So in a battery, yes, we do have a source of voltage at the core of the battery, EMF. But every battery also has inside it a small amount of resistance, which we call the internal resistance. So what this means is when a battery is in use, some of its potential from the EMF is lost in the internal resistance before the charges even get out of the battery. And the voltage at the battery's terminals, the positive and negative end of the battery, will actually be less than the EMF voltage that's at its core. Now, it's a little bit easier to explain this through a diagram, so that's what I'm going to do. Okay, so this dotted or dashed box represents a battery, and it's got a positive and a negative end at the top and bottom. And inside that battery, we're going to have, yes, a source of voltage, which is the EMF. But then in addition to that, and this is the part that we've sort of been neglecting up until now, there's going to be a little bit of resistance. So let's put some symbols in here. The symbol we use for the internal resistance is R, but because this resistance is a particularly small resistance generally, and because it's inside the battery, we tend to use a lowercase r for internal resistance rather than an uppercase one. And the symbol we use for EMF, this voltage at the core of the battery, is an E, but it's sort of a fancy handwriting script E. So that shows how every battery has a voltage at its core, which we call the EMF, and a little bit of internal resistance, which causes some potential to be lost. So it causes the voltage to drop before charges even get out of the battery. And one of the things I mentioned before is how the voltage at the battery's terminals will be less than the EMF. So I want to illustrate that in my diagram. The voltage at the battery's terminals is what you would get if you took a voltmeter and attached it to each side, to each terminal of the battery, to the positive and negative terminal. So that voltmeter is going to give you a reading, and we'll call that reading V term, the terminal voltage, the voltage from one terminal on the battery to the other. Now, I've said that this terminal voltage, when the battery's being used, will be less than the EMF, but how much less? Or even you could ask, how are these three new quantities I've talked about, the EMF, the terminal voltage, and the internal resistance, related to each other? Well, it turns out to demonstrate that, or to show that, we don't really need any fancy new math or equations. We can just do it using some of Kirchhoff's laws and Ohm's laws that we know already. So remember that voltage is a difference in potential. So this terminal voltage that I'm measuring with this voltmeter is going to be the difference in potential that I notice between here at one terminal and here at the other terminal. So to figure out what that number that's going to be, I can kind of trace the path a charge would follow from one terminal to the other. So as a charge kind of heads up this way through the battery, it's traveling along a wire, so no changes in potential there. It goes through the EMF, where it gets an increase in potential, just like a skier going up a chairlift. So a little increased potential by whatever the EMF is. And then when it goes through this resistor, it'll decrease its potential, just like a skier going down a run. So we have an increase in potential followed by a decrease in potential. And then we get to the other end of the battery, the other terminal. So how can I write that out sort of mathematically? I can say the terminal voltage, the difference in potential I'll get from one end of the battery to the other, is going to be, I'm going to go up as I trace through the battery by the EMF. There's an increase in voltage of E there. And then I'm going to lose some potential, so I got minus, as I go through that resistor. And how do I calculate the potential that I lose going through this resistor, the voltage drop through that resistor? Well, we can use Ohm's law for that. Ohm's law says V equals I times R. So the voltage I lose going through that resistor is going to be the current going through the battery times the resistance on that resistor. Now, please remember about this equation that it's really nothing fancy. We got it by just saying, as I go, the terminal voltage goes from here to here. And as I travel from one of those spots to the other, I'm going to go up a voltage as I go through the EMF and down some voltage as I go through the resistor. Up this and then down this. Now, most batteries that we'd be interested in aren't just sitting there. They're connected to some sort of circuit. So this battery probably has wires heading off this way, going to some kind of circuit, and it probably has some current flowing through those wires. And that's this current that we used over here. But something interesting happens with this equation we came up with. What if the battery isn't hooked up to a circuit? What if we have pulled it out of its device and it's just sitting there on the table? Then what would we expect this current to be? Well, if the battery's not hooked up to a circuit, if it just sits there, no electricity is going to flow, and that current is going to be 0. And if the current is 0, we can see that this part of the equation is going to completely go away. And we're going to be left with terminal voltage is equal to the EMF. This leads us to actually a useful way that you can measure the EMF of a battery. Because if you think of the EMF as being buried down here in the core of a battery, you might think that, oh, in order to measure that, in order to get my voltmeter in there, I'd have to like drill holes in the battery. But turns out that there's kind of a smart way to measure it. And that is you just pull the battery out of its device. So it's not connected to a circuit. So there's no current flowing. And then you can measure the voltage here and here, like you normally would with a voltmeter. That's technically measuring the terminal voltage, but as long as the battery's not delivering electricity, as long as there's no current, the EMF is the same as the terminal voltage. So you could find the EMF that way. Okay, one thing that's really important to note about EMF that you may have picked up on already, but you may not have thought about, is that electromotive force is not a force. So in that case, what is it? Well, electromotive force is a voltage. So why do we call it a force if it's not a force? Well, this kind of dates back to when electric circuits were first sort of being discovered and experimented with. People were a little bit unclear about exactly the physics going on inside some of these things. And although there is a force involved in causing current to flow, this thing they were measuring, this EMF they were measuring, wasn't actually that force. It was related to it, but it was a slightly different thing. Now, batteries are often characterized by their EMF. For example, a car battery has an EMF of 12 volts. A AA battery, and I use quotations here because you've learned now that those little AA things are technically not called batteries. They're technically called cells. And a battery is what you get if you combine two or more of them together. Anyways, any store will call it a battery, so we'll call it that. That will have an EMF of 1.5 volts. And those little square batteries, the ones that have the positive and negative terminals both on the same end, those have an EMF of 9 volts. So all these different types of batteries, one of the things that's often unique about them is the amount of EMF they have, the amount of voltage they have fundamentally down at their core. So EMF and internal resistance in these batteries, like this new thing that we've been talking about, it's not just important when we're using the battery. It's also important when we're charging a battery. Now, not all batteries are chargeable, but for the ones that are, let's look at how these new quantities sort of behave in that scenario. So to charge a battery, what you need to do is you need to hook it up to a power source, in other words, a charger, that is stronger than the battery is. And let me kind of draw a diagram to illustrate what I mean by that. So here's my, my drawing of a battery again. I've got an EMF, a source of voltage at the core of the battery. But before my charges can get out of the battery, they do have to go through a little bit of internal resistance that's built into the battery. And if I want to take this battery and charge it, that means rather than having current come out of the battery this way and head off into a circuit, I need current to actually go from a circuit back into the battery this way, which is tough because this EMF is clearly pushing current. I shouldn't say pushing because it's not a force. It's causing current to want to go this way. So how do I make current go the other way? I'm going to have to get another EMF that's trying to cause current to go back the other direction. And that second EMF needs to be stronger than this one. And that's going to be my charger. So over here, I have another EMF. That I'm hooking up to my battery. That's going to try and charge it. So this is going to be the voltage of my charging device. That's going to push current back into the battery. And because the charging device is directly connected to the two terminals on the battery with no resistors or anything in between, that means the voltage across that charger is going to be the same as the voltage at the two terminals of the battery. So I can actually call the voltage on that charger, I can call it the terminal voltage on the battery. So if I use a 15 volt charger, the terminal voltage on the battery will be 15 volts. If I use a 20 volt charger, the terminal voltage on the battery is going to be 20 volts. And then as before, this internal resistance on the battery, we'll give that the symbol lowercase r. So how are these quantities all going to be related? Well, because my charger is stronger than my battery, we are sending current, forcing it back this way into the battery. So that means because my current is now flowing this way through my internal resistance, that means as I go down through that internal resistance, I'm losing potential. So I'm losing potential going in this direction. So this is sort of like the downhill direction. From top to bottom, I'm losing potential. I'm going downhill, you can imagine. So then, if we want to look at the terminal voltage of the battery, comparing the voltage at this end to this end, well, as I travel from bottom to top, I'm going to gain some EMF, and then I'm actually going to have a gain in voltage as I go through the resistor, because I'm basically going Remember, going down through this resistor was considered the downhill direction. So if we're going up through the resistor, it's kind of like we're going uphill, and we're going to gain height or gain potential. So let's write this out. The terminal voltage, as you go sort of from the bottom to the top of the battery, you're going to gain some voltage from the EMF. And then you're going to gain, so we have a positive sign here, some voltage as you go through that internal resistor. Again, this is going to depend on the current you're getting. The voltage in that resistor is going to be current times resistance. And note, this is really very similar to the mathematical relationship we got up here when we were using the battery. Only up here we had a negative sign, and down here we now have a positive sign. And so this formula kind of serves as a reminder that when we want to charge a battery, the voltage we put at the two ends, the terminal voltage, is going to have to be bigger than the battery's EMF. It's going to have to be equal to the EMF plus a little bit. And that's to make sure that the charger can force current back into the battery, and we don't have the opposite situation where the battery is trying to charge its charger. So let's try a couple examples now. A 1.5 volt AA battery has an internal resistance of 0.22 ohms. What is the terminal voltage of the battery when a current of 0.5 amps flows through the battery? So I'm going to draw this out. So when we're calling the battery, when we're naming it a 1.5 volt battery, that's going to be a reference to the EMF, the voltage that is baked into this battery, the voltage that does not change at all over the course of the battery's life. So that part of the question tells me here that this EMF is 1.5 volts. And then it says we have an internal resistance of 0.22 ohms. And there's a current flowing through the battery. So sounds like this thing is hooked up to some sort of circuit. Don't know what the circuit looks like, but we don't need to. And we've got a current heading out into the circuit of 0.5 amps. And we want to know the terminal voltage on the battery. So basically, if we were to take a voltmeter and connect it here and here, what would we measure that terminal voltage to be? So voltage is a change in potential. So when looking for the voltage between these two terminals, I'm basically going to try to see how much the potential changes as I go from one of those terminals to the other. So what that's going to look like is I'm going to have obviously an increase in potential as I go through the EMF here of 1.5 volts, and then a decrease in potential as I go through this resistor. So I start with this increase in potential from my EMF, and then I'm going to lose some potential as I go through the resistor. How do we calculate the voltage drop on a resistor? Well, Ohm's law, V equals I times R. So then if I plug in some numbers, 1.5 for the EMF, 0.5 for the current, and 0.22 for the internal resistance. So the terminal voltage on the battery is going to be 1.39 volts. Now this next example, we are charging a battery, which actually reminds me of something I wanted to say earlier, which is that when a battery goes dead or needs charging, it's actually a little interesting why that happens. You might think that when a battery goes dead, it means it's got no more voltage left in it to kind of cause current to go. The common misconception is that means the EMF is now zero in a dead battery. And that's not true. In a dead battery, the EMF is usually just as strong as it always was. In a dead car battery, the EMF is still 12 volts. In a dead AA battery, the EMF is still going to be 1.5 volts. So what is different inside a dead battery that makes it so useless? Well, turns out in a dead battery, it's not that the EMF has decreased, it's that the internal resistance has increased. So although we still have in a dead battery the same increase in potential from here to here, we're going to have a huge decrease in potential as we go through that internal resistance, because the resistance has become so great that if you just look at the voltage from one end of the battery to the other, from the terminal voltage, you're going to see a voltage there that's actually very small and not sufficient to do anything with the battery. But it's not because the EMF is smaller, it's because the internal resistance is so much bigger. Okay, so on the topic of dead batteries, let's look at a question where we're charging a battery. A 12-volt car battery is being charged by an alternator. Alternator is just the name of the device inside a car that charges its battery. And that alternator is supplying, that charger is supplying 15 volts. The internal resistance on the battery is 1.3 ohms. What is the current through the battery? Let's draw this out. So here we're going to try and find the current, and we're going to do that using Ohm's law. We've used this a few times on this lesson, but we haven't always written it down. And when you use Ohm's law, you have to decide on a point where we're going to use it. So I can't use Ohm's law here because I don't know any resistance. There isn't any resistance. I can't use Ohm's law here because there isn't any resistance. The only place I can use Ohm's law is somewhere where there's a resistance, and that's going to be there. So I'm going to apply Ohm's law there. But to do that, I know the resistance at that point. I'm going to try and find the current. So I'm going to need to know the voltage across that resistor. And to show you what the voltage is going to be across that resistor, I'm going to use the skiing analogy here a bit. If we start by looking at this bottom wire here, we've got these two power sources that are attached to it. One that brings me up 12 volts through this chairlift to the bottom of the resistor, and one that brings me up 15 volts through this chairlift to the top of the resistor. So if I have to go up 12 volts to get to the bottom of the resistor and up 15 volts to get to the top of the resistor, what's the difference in potential going to be between the top and bottom of the resistor? Well, it's going to be the difference between 12 and 15. It's going to be 3 volts. So looking at that resistor, I can say I have a voltage across the resistor of 3, and the resistance in the resistor is 1.3. So that gives me a current of 2.31 amps. And one thing you might notice is we could have got this exact same answer by sort of using the work we did up here and using this sort of formula that we came to for charging a battery by plugging these values we have down here into that formula. We would have come to this same answer here. And that's effectively what we did, only we sort of, rather than reusing the formula, we just went through the steps ourselves, which I think is sort of the better way to do this stuff. So that's EMF in a nutshell. Basically, the Coles notes are every battery has a voltage at its core, which we call the EMF, but also a little bit of resistance before you get to the outside of the battery, the terminals of the battery. And you can figure out how a battery is going to behave in a circuit by drawing it out with that EMF and that little bit of resistance, and then by just using Kirchhoff's laws and Ohm's law to figure out currents and voltages where you need to.